going back, I'll make a correction that was already made during the discussion section, but I'll do it for the benefit of the camera and the million people watching on YouTube. So if you remember, at some point we were deriving the integrated Boltzmann equation from the collision operator for the WIMP. And I wrote something like this. But this is false. And indeed, if you try to derive the Boltzmann equation using this, it's not going to work. The correct equation has the integral over the same phase space on both sides. And indeed, okay, if you try to prove the first equality, you will never succeed. While this equality is completely trivial. It's a consequence of the fact that the dagger of the absolute value squared is the same as the absolute value squared. So I encourage you to try if you haven't seen it yesterday in the discussion session. Okay. So setting this correction aside, let me write down again for you the list of, let's call them exceptions to the WIMP calculation for historical reasons. And then, well, if any of you feels brave and wants to try to solve the puzzle at the end of the last lecture, we're going to try. And if not, we're going to keep moving and talk about more of these exceptions. So we've seen in some detail that you can change the kinematics. So you can keep your 2-to-2 process. But imagine now that the mass of the standard model particle that dark matter is annihilating to is bigger than the dark matter mass. And about this, so I should add that if you want to do with an annihilation to standard model particles, you're going to populate small regions of this plane. So let's say you have the dark matter coupling and the dark matter mass. So the usual WIMP prediction is some line if these two axes are in log scale. And this process will give you some regions where you can have a much larger coupling. But these regions are concentrated around some standard model particle mass. I don't know, say the muon mass. And the reason why the mass split cannot be too big is that if the exponential suppression becomes too large, then some loop couplings might dominate. So let's say that, I don't know, you have annihilation into muons. Just to give you an example, I mean, you can always close a loop and have neutrinos. So the moment that this diagram dominates over the exponentially suppressed one, then the exponentially suppressed one becomes irrelevant. All that matters is the last diagram that freezes out. So if you really want to play this trick within the standard model, you are, in some sense, predicting very precisely the dark matter mass if you want to give a positive spin to the idea. However, you can do this also in a dark sector. So you replace your standard model particle with some new particles psi. And if psi is sufficiently weakly coupled to a thermal butt of radiation, then in principle, you can find the right dark matter relic density in all the upper half of this plane. And after seeing a couple more of these exceptions, I'm going to tell you what are the boundaries of this plane. Because, okay, you might have noticed that I haven't put any labels on this axis. So where is this ending? So in principle, there is no conceptual limitation to the power of these mechanisms. Or even in the WIMP case, you can keep making the coupling smaller and smaller and having the mass smaller and smaller. But at some point, you hit some observational bounds. And we're going to talk about them today. So other than the kinematics, you can change the dynamics. So for example, you can consider 3-to-2 scattering. Of course, in this case, you have to explain why 2-to-2 is suppressed. And well, a well-known example of these are the so-called strongly interactive massive particles, or SIMPs. So I'm going to give you a very, very quick rundown of how this works. And the original idea was by a collaboration mostly based in Israel. And well, it goes in the following way. So imagine that this is the nominal process that is changing the dark matter number density. So here you have only dark matter particle. This is obviously a toy model. So if you want to see a complete model where this is really the dominant process and the 2-to-2 processes are suppressed, I invite you to look at their paper and their follow-up. But let's imagine for a second that this is really the case, so that this process dominates the number-changing interactions of dark matter. In that case, well, the Boltzmann equation that we wrote yesterday is going to look like this. And then, well, we can, to understand what's the prediction of this model, we can use the same strategies that we adopted yesterday. So again, when the expansion of the universe dominates over the interactions become irrelevant and the number of particles is conserved. And so there is also in this case a moment that we can call freeze out when these two terms are comparable. And from that, you can derive how much dark matter we expect to have today. And well, the only thing to keep in mind here is that a 3-to-2 interaction cross-section parametrically doesn't scale like a 2-to-2 cross-section. So you can even see it just by looking at this equation. So for the dimensions to be correct, you cannot write this object as a coupling squared over a mass squared anymore. But the right parametrics are a coupling cube over a mass to the fifth. And if you take the same steps that we took yesterday and compare the number density at freeze out with the number density that we expect for dark matter today by redshifting it, et cetera, you're going to find that for couplings of order 1, you expect masses of order MeV. And the authors in a fantastic marketing realization, well, notice that this is what you expect from QCD, so they called it the SIMP miracle, because it's not so different from the WIMP miracle. And I leave you as an exercise the derivation of this result. Of course, okay, there is something hidden here, right? So if this was the whole story, you would immediately run into a problem, because this 3-to-2 process was actually considered first in the 90s by all Machacek and collaborators. And you can see immediately what's going on here. So if this process is efficient, you're effectively converting mass into kinetic energy. And so this dark matter sector becomes very hot very rapidly. So if there is no connection to radiation, and this is really the whole story, so a dark matter particle sitting in isolation turning 3s into 2s, then you would have a problem with structure formation, because this sector would immediately become very hot and disrupt some of the standard model predictions that work so well today. And so you need somehow a tiny coupling of dark matter to radiation. I don't know, you can add some dark photon or or any other mediator that connects it either to the standard model or to some light particle. But somehow you have to do it in such a way that these 2-to-2 processes that keep dark matter in kinetic equilibrium with the thermal bath do not dominate over this 3-to-2 interaction. So you have to construct your model carefully if you want this to be the parametrics. And this is true a bit everywhere when you play these games and you extract either exponential or power law suppressions compared to the WIMP. There is always a small coupling hiding somewhere. Also in the case of forbidden, and I invite you to look for it as an exercise again, and you're more than welcome to tell me once you found it. Okay, so yes. A small mass, sorry, I cannot hear you very well. A small mass?
We're going to have small masses for dark matter particles.
Yes, indeed. So if they're strongly coupled, then you expect them to be lighter than a WIMP. Yeah. I mean, even if you go to order weak scale couplings, still the mass is going to be, I think, smaller than a WIMP. So you can just check by using this relation, so this parametric relation. Okay, so the other thing we said that we could change is the thermal history. And well, the most modern example of this, it's called Cannibal dark matter. By this set of authors. And which is building upon the paper by Lawrence, Sol, and collaborators that I mentioned before. So you will see that this 3-to-2 interaction is not exactly ubiquitous, but it appears often in these exceptions. And the basic idea is that you're going to imagine that there is a dark sector that's completely decoupled from the standard model. So this is the dark matter sector. It has some temperature, T dark. And then there is the standard model, which has some temperature that is the photon bath temperature. And here we are going to imagine that the dark sector has no kinetic equilibrium with a bath of radiation. We're going to imagine that there is a mass gap, meaning that, there are no massless particles in this sector. And we're also going to imagine that there is a process that keeps dark matter in chemical equilibrium. I'm not going to write explicitly a model, but actually, if you just take the same that we did for the SIMP and do not couple dark matter to radiation and imagine there is no massless particle coupled to it, then you get this. You get these three conditions. I just wrote them in general because, in principle, you can imagine different models. Let's say that these conditions are satisfied, and the fact that the two sectors are decoupled is due to the fact that in the standard model we do have a massless particle, so coupling them would effectively couple dark matter to a bath of radiation. So if this is the case, you might wonder how is the temperature of the dark sector compared to the temperature of the standard model. And you can again use conservation of entropy, this time separately for the two sectors. So that's the entropy in the dark sector at some time 1 is going to be equal to the entropy in the dark sector at some time 2, and similarly in the standard model. So also the ratio, so if you take the ratio on these two sides, you're going to find that the ratio between the entropy densities in the two sectors is constant. Okay, and we said that there is no mass gap here, so there is some smallest mass scale, let me call it MD. And at some point, well, since the universe is still a collection of particles and radiation, the temperature will keep decreasing as the universe expands, and at some point, it will become smaller than the smallest mass scale in the sector. This means that, as we've seen on the first lecture, all the relevant quantities, in particular also the entropy density, will be exponentially suppressed. So when this time arrives, the entropy density will look something like this. And so if we imagine, as we said yesterday and the day before, the entropy density times the scale factor cube remains constant because of the fact that we are in equilibrium, so the entropies are conserved. So this means that this object will scale like 1 over the scale factor cube. And so if we solve for the temperature as a function of the scale factor, we're going to find that the temperature in this dark sector, after you cross this mass threshold, is going to decrease as log of the scale factor. However, in the standard model, everything that we did yesterday still holds. So the temperature of the standard model keeps going like 1 over A. And so very rapidly, this sector will become much, much hotter than the standard model. They're still both becoming colder, but this one is becoming colder only logarithmically. So if here we put the standard model temperature, 1 over the standard model temperature, so this time increases in this direction, then, okay, of course, the standard model temperature will go down like that, and instead, the temperature in the dark sector will go down much more slowly. And again, these are log scales. So here there is a huge gap at some point. And yes? So if you add dark radiation to the sector, then this will not be true anymore. So if you add dark radiation, which is, so if you read all this sector, so if you have energy density into the dark radiation as well, so when this happens, the dark radiation will dominate the energy budget of this sector, and so this will never occur because the total entropy density of the sector will still go like T cube. Yes?
And there is kinetic equilibrium in the dark sector, right?
No, there is no kinetic equilibrium in the dark sector because so by kinetic equilibrium I mean that a massive particle has the same temperature as a massless particle in the same sector. But I'm explicitly asking that there is no massless particle in this sector.
Okay, and in that case, how do you define temperature for the dark sector?
Yeah, so you can do it by so in several different ways, but let's say the simplest, most natural way is to define an effective temperature starting from the kinetic energy of these objects. So these dark matter particles will still have a momentum distribution. And so you essentially average p squared over E times the momentum distribution, and that gives you something proportional to what I'm calling a temperature. But okay, yeah, so if you want, like the important invariant quantity is that the entropy density is becoming exponentially small. So in some sense, this sector is starting to dominate the energy budget of the universe. And so if you work out, so let's say you now repeat a freeze-out calculation, a WIMP-like freeze-out calculation in this sector, you'll find that you need much larger couplings. So again, there is an exponential hidden here. So there is a log versus a linear object. And you will see that you need much larger coupling to get the right relic abundance of dark matter if dark matter lives in this sector. Yet another thing that, yes?
How is this not a problem with structure formation?
No, indeed, it's a problem. So at some point, you have to stop. So at some point, so you might wanna. So one way to stop this is that you add a very tiny coupling of the dark sector to the standard model in such a way that at some point these massive guys decay. Okay, but this will happen only. So if it's really the decay that dominates, this will happen only when the decay rate is comparable to Hubble. So you can have like a period, and then this thing like goes down sharply. So indeed, actually, so if you are interested in an historical note, these guys, so in '92, this was still consistent with structure formation. So they proposed this idea to mess with structure formation and do something interesting. And instead, okay, well, 15 or so years, no, sorry, almost 25 years later, now we have to add this coupling and stop this after a short amount of time. I mean, you cannot have many e-folds of this process. Yes?
I didn't get why a nice idea to make the dark matter cosmic.
I mean, okay, so I want to try to avoid, let's say, judgments. It's just another possibility where the parametrics differ compared to the standard calculation I showed you. So it's just an example of something that might be different in the history of the universe compared to what we usually assume. And so this is a conceptual possibility, and if it's realized, then you're going to have you're going to need much bigger couplings of dark matter to get the right relic density, but much bigger couplings to the dark sector. So in practice, for us, it will look weakly coupled. Yes.
One more question. What is now the difference between case 2 and case 3? Because you in case 3 also assume number changing process because the chemical equilibrium otherwise would be like the chemical potential could be 0.
Yeah, so the difference is mainly this one. So in case 2, I didn't write it explicitly, but there are some interactions that keep chi in kinetic equilibrium with the standard model, okay? Let's say something like this. So as you do this calculation, for example, this number density here, if it's in equilibrium with the standard model temperature. So the sector never becomes hot. So it's always tracking the standard model temperature, because even if this guy is effectively increasing its kinetic energy, then this process is dumping it into the standard model. And since this whole story, it's happening early on in the history of the universe, the dark sector is a tiny amount of the total energy density of the universe compared to the standard model. So even if there is all this kinetic energy dump, the standard model doesn't even care. So like for the standard model, it's like 10 to the minus 12 or less of its total energy density that it's being dumped into it. So it's like, it's like putting, I don't know, a tiny hot thing in a gigantic fridge.
So in that case, there is no cannibalistic dark matter in that sense.
Yeah, so well, I mean, to some extent, yes, but you don't see it because the extra kinetic energy gets cooled down by the standard model bulk. In practice, I mean, they are effectively the same model, only you make this coupling much smaller in what you call Cannibal. Okay, so if there are no more questions, so unfortunately I've finished the blackboard, so I can either start from the beginning or delete that stuff. So I don't know, well, for maybe it's better if I start from the beginning so you have that stuff. Okay, good. Okay, so number 4. Let's see how many more we have. Well, we have a couple more after this. So number 4 is that we can relax the hypothesis that you have only one dark matter particle. And I would say that this is the best known of the exceptions to the standard calculation. it was already pointed out by Grist and Saclay in that paper from the late 80s. And then, okay, it played a huge role in supersymmetry because you can mix Winos and Xenos and see what comes out. So there are a gazillion papers on this idea. But, okay, well, more recently, we've shown that you can, again, leverage these exponentials to their fullest. But at this point, okay, it's not that exciting anymore. You've seen now where the exponentials come from. I'm just going to tell you this because, in some sense, has been central in the history of particle physics, given supersymmetry. So now we're going to imagine that we have some number of dark matter particles. And in the end, what we really care about is just the sum of their number densities. The reason is that we're going to imagine that they interact with each other. So eventually, the heavier ones all decay to the lightest ones. And our notation will be such that they are ordered. So particle number n is the heaviest, and particle number 1 is the lightest. And since we care about only the sum of the number densities, we can write a single Boltzmann equation. So and we can do better and rewrite it. So I'm going to write it up here. You can rewrite it just as some effective cross-section times the total number density. If you want, you can try to do it as an exercise. It's just a little bit of algebra with which you can show that this effective cross-section can be written in the following way. Which roughly, so if these particles are non-relativistic, so in the regime relevant for freeze-out, this becomes the following. So essentially, an average cross-section with weights proportional to the effective number of degrees of freedom of each particle and factors that depend on the masses. So I'm going to go here times e to the minus . And so these deltas are defined like we did yesterday. So delta J will be mj minus the mass of the lightest particle divided by the mass of the lightest particle. And x is, again, 1 over the temperature in units of the mass of the lightest particle. And so, well, okay, you already see where the exponentials are coming from, because, for example, you can imagine that, I don't know, the heaviest particle is the most strongly coupled. So then the effective cross-section is going to be dominated by the heaviest particle. And so again, there is an exponential suppression, and this changes exponentially the prediction for the cross-section that you expect to get the right relic abundance. So again, you can repeat the steps that we followed yesterday and compare, if you want, this effective cross-section to the WIMP. In practice, you're going to find that again, so the chi energy density today is going to be proportional to 1 over this cross-section, which now, compared to that of a WIMP, is exponentially, so at freeze out, is exponentially larger, and so you will need different couplings. Sorry, it's exponentially smaller, so the relic density is exponentially larger for the same coupling, and so you will need bigger couplings. Of course, this is just one special limit, if you want, right? So because we've imagined that the heaviest one is dominating, but there are many different limits of coannihilation. So it's not really right to say that coannihilation always predicts this. It's just another way in which you can change the prediction of a WIMP exponentially, but it can go in different directions depending on which ones of these particles dominate the cross-section. Okay, so now we are left with the last two, which are respectively the easiest and the hardest to guess. So the fifth thing that you can change with respect to the WIMP calculation is just the coupling. Okay, so we were at the end of the calculation effectively assuming that this is comparable to weak interactions. So it's not too far from being order 1. But okay, as we've seen by now multiple times, the WIMP calculation is really just telling us that we're living in this line, in this log-log plane. So if you have a way to decrease the coupling of dark matter to us, keeping this ratio, keeping this ratio that's proportional to the cross-section fixed, then you're going to still get the right relic density. And there is a very, let's say, elegant way of doing it, which is known as the WIMP-less miracle. By Feng and Kumar in 2009. And I encourage you to take a look at the paper, but the basic idea is very simple. Essentially, you have SUSY breaking that is gauge mediated both to us and to some dark sector. And the gauge coupling of this dark sector is very small, but gauge mediation precisely fixes this ratio, so the gauge coupling over the mass of the SUSY particles. So if in our sector, SUSY breaking gives you roughly weak scale cross sections, it will do the same also in this other sector, even if this other sector is much lighter and more weakly coupled. So if you want, this is like a UV complete way of living on this line. However, there is also something, let's say, more drastic from the point of view of dark matter that you can do by changing the coupling, which is the following. So imagine that the coupling between the dark matter sector and us is so small that if you put energy only in the standard model, you never appreciably populate the dark sector at early times. So at early times, something is reheating the standard model, but then the coupling is not big enough to generate an observable energy density of dark matter. So you can imagine that initially, the dark matter number density is 0. So at this point, you can write, so if you imagine again that the main connection between the two sectors are 2 to 2 processes, you can write the same equation as the WIMP. only this time you only have the inverse process. So standard model going to dark matter times a number density in the standard model squared. So the process that depletes dark matter is not efficient because you don't have dark matter particles, so you cannot have two dark matter particles meeting each other and dumping energy in the standard model. So you have only this side of the equation. And let me further imagine so that the standard model particles involved in this calculation are light at freeze out. Okay, so if this is the case, our freeze out calculation now looks like the following. So Nk at freeze out is going to be roughly equal to the cross section divided by Hubble at freeze out times a number density squared of a light particle. So this goes like the temperature to the 6. So overall, you're going to have something like coupling of dark matter squared times freeze-out temperature to the 4th times m Planck over m dark matter squared. Right? So, yeah. So this one, so to the 5, yes. So this looks like it has the right dimensions because you have energy to the 5 on top, energy squared below, and the number density is an energy cube in natural units because it's 1 over the volume. And so now, if you want, you can deduce some parametrics. So I'm undecided whether to leave it to you as an exercise or not. But maybe we can do it, I think. So we can, well, I will just give you the final result, and then you can take the steps on your own, since we've done it a few times now. So now you have to redshift this to today, compare it to the dark matter energy density. And so when you have, when you compute this ratio today, given this result here, you're going to have some m dark matter. So let me again now call this again sigma 0. The cross section times m Planck freeze out temperature, because power cube of the freeze out temperature is redshifted away by the expansion of the universe, and it turns into a temperature of today cube that then you simplify with the dark matter energy density, all divided by an electron volt. And you want this to be roughly 1. And so if you do the calculation, you will find that this predicts a dark matter coupling of order 10 to the minus 14. So this is, if you want, a more dramatic example of changing the coupling. So finally, okay, we're left with the last. Yes. Yes, yes. So this is a rough parametric estimate which gives you the result at order 1. If you want the precise result, you need to solve the full Boltzmann equation. But in practice, what you're going to see is, so if you plot the dark matter yield versus 1 over temperature, and this is the equilibrium distribution. So freeze-in looks a bit like this. So it will be much smaller than the equilibrium distribution, so negligible for the Boltzmann equation for most of the time, and then only close when it freezes out, it will track the equilibrium distribution. So you're making a small mistake by doing this approximation.
The small problem
Sorry? Indeed, so if the coupling, so I don't know if I heard the whole question, but I'll try to answer anyway. So if the coupling was big, then this process would happen much faster. So you would start tracking equilibrium much earlier on, even if you started from 0. So it's what we were saying yesterday, that if you have a large enough coupling, you're kind of insensitive to initial conditions, and the WIMP calculation becomes valid. So I don't know if that was the question. Okay, but we can continue offline, or you can shout louder. No problem. Okay, so the last exception that I wanted to mention is the one that I left you with yesterday. So I'm going to call it relaxed kinetic equilibrium, but in reality, it gives you something parametrically different from a WIMP, even if kinetic equilibrium is realized. And schematically, I was proposing to you this diagram. And again, I'm going to imagine that the standard model particle here is much lighter than a dark matter. So at freeze out, it's effectively relativistic. So at the end of yesterday's lecture, I had asked you 2 questions. So the first one is where the exponential coming from here, and the second is why, if this was the only diagram changing the dark matter into something else, it would be doing effectively nothing. So you want to try to answer one of the 2 questions or both? Yes?
I think you can get exponential suppression just by having chi lighter than phi.
That's indeed one.
But then the problem is phi decays into chi.
Yes. But, well, you can have, so psi decays into chi, yes. So, but why is this a problem?
Because you're recreating psi.
Exactly. So the problem is that this diagram is doing nothing because you have a conserved, well, so what you said is true. The more invariant way to say it is that this is a conserved quantum number in this theory because there is nothing that is breaking this U1 symmetry, if you want. So that's right, but there is another exponential hiding here that goes in the opposite direction. So if you want to try, or anyone else wants to try, and the key is what I just said. So in the hierarchy of masses between the particles here. So. Okay, well, I'm just going to tell you. So, yes.
They are non-relativistic, so they're washed away.
No, but yeah, so the chi's are non-relativistic, but it's the same. So also for the WIMP, they're non-relativistic at the, let's say, crucial time of freeze out. So, but there is something that is different from the WIMP. Okay, well, when I say it, you'll see that it was easier than you thought. It's just that I said at the beginning that the standard model particle is light. So it's going to be relativistic at freeze out. So the relevant rate for the WIMP is something like this, where chi is non-relativistic. So this n chi at freeze out is exponentially suppressed. But if this diagram is the one that is determining the dark matter relic density, let me call it co-scattering, which is the name, oh sorry, this square should not be there, which is the name that we gave to this idea. Well, actually, Lawrence Soul suggested for this idea. Then here, so the relevant rate depends on number density that is exponentially suppressed, but a number density that instead is is relativistic, so that n standard model is going to be just a temperature cube with no exponential suppression. So finally, you're going to find that to get the right relic density, you need a co-scattering cross-section, which is exponentially smaller than that of the WIMP. And so this mechanism, in some sense, it's populating the lower half of this plane. So here you have the WIMP, or WIMPless, or whatever you want to call it along the line. Here, in principle, you can have forbidden, and down here, you can have co-scattering. Okay? Of course, there are other ways of doing it, but actually, as far as I know, co-scattering is the only one that can, in principle, populate most of this plane. And of course, so as I said, this cannot be the whole story, because this diagram is doing nothing to the dark matter relic density. So for this parametric result to be correct, you also need to dump psi's into radiation. So you need some coupling of psi, for example, to the standard model. And, well, you can, for example, realize this if chi has a tiny mixing to psi. So let me call it delta, with delta much smaller than 1. Okay? So if this is the case, so if there is this process and this process, then you can realize this mechanism. Again, I'm going to start from the top. And so the nice thing of this picture is that it's going to show you that all these exceptions that I'm telling you about are, for the vast majority, all connected to each other. So it's not something that we kind of invented out of the blue, but if you write down a generic model, they appear as phases, in some sense, of freeze out. So you can kind of draw a phase diagram of freeze out as you do for phases of matter. And let me give you a schematic picture of why this is the case. So let me say that you have some chi particle that has a small mixing with some psi particle, which has some order 1 coupling to the standard model, okay? Then, okay, in this model, you're going to have all sorts of processes. You're going to have co-annihilation, so chi and psi annihilating together. You're going to have chi annihilate on its own. And you're going to have psi annihilate on its own. And of course, you're also going to have all these diagrams rotated by 90 degrees. So you have all possible forms of scattering. And depending on the value of this small parameter, you are in different phases of freeze out. So this is delta. So if delta is very big, so that chi is coupling at order 1, and let me add another thing, that the mass of psi is bigger than the mass of chi. Okay? So if delta is very big, essentially you have a WIMP, because chi is interacting with the standard model at order 1 on its own. Psi is heavier, so it freezes out first, and there is only a small amount of psi compared to chi. So whoever freezes out, so in this case, the amount of psi should be added to the total amount of dark matter, but it's going to be a small amount. So in practice, if you compute only this diagram, you're going to get the right relic density modulo small corrections. If you keep making delta smaller, then there is going to be a regime in which this diagram starts being important, because the exponential suppression that you get for having an extra psi in the initial state with respect of 2 chi's it's going to be compensated by the small extra mixing that you have in this diagram, right? So if you look, so the diagram, this diagram goes like some cross-section times n chi squared times delta squared. This diagram goes like some cross-section times delta times n chi m psi. So if you take the ratio of these two, you're going to have that the above diagram goes like e to the minus m psi minus m chi over temperature times delta. So when this delta becomes smaller than this exponential suppression, then you have to take into account also co-annihilations. So this diagram and possibly also this diagram to compute the chi relic density. And so as you make delta smaller, you are in a co-annihilation regime. Okay? Then you can make delta so small that so that this diagram becomes completely irrelevant, and that also this diagram becomes completely irrelevant. But this one will still be important because it has a delta suppression and also a small exponential suppression from the mass difference between chi and psi. But in the initial state, you have a relativistic particle. So with respect to these two diagrams, you are gaining a big exponential factor. So not the mass difference, but a full e to the minus m chi over t that you're gaining from considering this diagram instead of these two. And so as you make it even smaller, you end up in co-scattering. If you add, say, some other axis to this plot with a coupling or a mass ratio between mediators and dark matter, you can even have other phases. So you can like carve out a region here of the WIMP that becomes forbidden, but okay, I don't want to enter too much into the details. This was just to give you an idea of how, in some sense, freeze out organizes itself like a phase diagram. Sometimes you're not inventing a model, but you're just finding that you were doing the calculation wrong. Okay, so I'm already past half time. So I think it's a good time to stop and see, well, if you guys have some more questions. So you asked already a lot, so if you don't, of course, no problem. Yes?
So, one of the main points here was that, this n chi plus n phi is conserved.
Yes.
If I lower the mass of chi and psi at some point, I can become kinematically forbidden to go from psi to standard model for chi. So I do lose the exponential suppression because then it's not that different anymore, the masses, so I don't have that exponential suppression number, but I have one, the original one.
So you, sorry, let's say that again. So you want psi to be so light that this process is forbidden.
Yes.
Okay.
So then you have this exponential suppression on the chi standard model with psi standard model, but you don't have the other one, but still.
Yeah. So, but yes. So you don't have this exponential suppression. You still have this exponential enhancement in the diagram. But now, so, well, let me see what exactly you want to do. So you want, so if you have this diagram, you're going to have also this diagram. Okay. Well, okay, you can still say that, let's see, so if this, so in the picture that you've drawn, the dark matter number density now is the sum of the chi and psi number density. So this diagram becomes irrelevant because it's not changing the sum of chi's and psi's. So you don't have to consider it anymore for your relic density calculation. And so now you are in a regime where one of these, so one of the 3 diagrams that I've drawn there matters. So in this limit that you described, you are doing coannihilation, which, so some limit of coannihilation. It could be WIMP-like or more like weird, like the one that we drawn on the board, but you're still doing coannihilation. Actually, now that you asked the question, I noticed that there is a definition missing in my coannihilation blackboard, because I didn't tell you what G effective is. Well, you can kind of imagine it. So it's essentially a number of degrees of freedom weighted by, again, these number densities, but I'm going to write it down for completeness. Okay, so yeah. Do you guys have more questions? So as you think about it, I will use the time to delete some of this stuff. So, okay, so far I've told you some ways to make dark matter much lighter and more weakly coupled than traditionally expected. So this quick review was just meant to pique your interest, because if you really care about these ideas, I recommend you go and read the papers, because as I said, so this very quick parametric discussion hides the fact that there are some small coupling and some model building to be done to realize these scenarios in practice. So it's for you to judge if you consider them on the same footing as the WIMP or not. Personally, well, I wouldn't say that they are exactly as simple as a WIMP, but I would say that they're still worth looking for, especially given that we've been looking for the WIMP for decades. And now it's not so easy anymore to have, well, okay, there are some examples left, like Exynos, but the most vanilla WIMP possible that you can imagine, a charged, a neutral object coupled to the Z is long dead. Even the second simplest thing that you can imagine, some neutral object coupled to the X is excluded by direct detection. So we're now starting to move into loop region. So it's a good time to start considering alternatives. What we're going to do next is to attach some numbers to the plots that we sketched on the blackboard. So I'm going to tell you how small of a mass dark matter can have in this thermal scenario. So you can see that we've almost always considered production through a Boltzmann equation. So there is some reservoir of energy density sitting around in the universe, and you're making dark matter out of it. However, this doesn't allow us to even remotely saturate the experimental bounds that we have on the dark matter mass. So the lightest the dark matter can be in these scenarios that I've just described is a kilo electron volt. And I'll tell you why. So actually, in the simplest ones, it's even heavier. It's a mega electron volt. And the reason, well, the reason is purely observational and relatively simple. So as I anticipated to you a few times, we have a precise measurement of the expansion of the universe, so of the Hubble parameter, when the temperature was a mega electron volt. So we know that at this temperature, the universe looked like the Standard Model in thermal equilibrium. So by thermal, I mean both kinetic and chemical. So the Standard Model particles were in equilibrium with photons. And we have a very precise determination of Hubble at this time, which is often phrased in terms of a delta N effective parameter. And this is defined as the energy density into anything new divided by the energy density into one Standard Model neutrino. The definition historically comes from the fact that N effective is supposed to count how many effective neutrinos you have at a given time. So delta N effective is the difference between the number of neutrinos that you expect in the Standard Model and the one that you actually observe. And we have a bound at this time that is of order 1. So roughly, this delta N effective should be smaller than 0.5, very roughly, okay? The reason why, so if you think about it, this is pretty amazing. So we are saying that we know at order 1 the content of the universe when the temperature was 10 to the 9 times smaller than today. So going back 13 billion years. The reason why we have such an amazing determination of the energy budget of the universe at that time is that essentially all, so neutrons, so weak interactions froze out at this time. So if you compare the rate of weak interactions, which is roughly the Fermi constant squared times the temperature to the 5, because there are still weakly interacting particles that are relativistic in the Standard Model at that time, with Hubble, you're going to find that freeze out occurs when T is roughly a mega electron volt. And since the weak interactions are those responsible for making nuclei decay, essentially if you have some light elements today, like lithium, deuterium, 4, these froze out at this temperature. So the amounts that we have today in regions that are poor of stars can be traced back to this time in the history of the universe, exactly as we did for dark matter. So we can do a phase-out calculation for, say, helium-4 and redshift it to today, and the prediction of the Standard Model is in great agreement with observations. And, well, the interesting fact is that essentially you can show that all neutrons that were around at this time turned into helium-4. And the amount of neutrons divided by the amount of protons that you had around at this time is, not surprisingly, since the temperature is smaller than their mass, exponentially sensitive to the temperature. So let me call this T freeze out. Okay, and this T freeze out depends on Hubble at that time. And Hubble at that time, as we've seen yesterday, depends on the total energy density floating around. So in practice, we're saying that we are exponentially sensitive to the energy density that existed at that time. And that's why we can set such a bound. In practice, what does it mean for dark matter? It means that all the models that we've seen where the dark matter temperature is the same as the Standard Model temperature at that time, so when T gamma was MeV, need to have a dark matter mass bigger than roughly a mega electron volt. Because otherwise, so if the dark matter mass was smaller than this temperature, then it would contribute to the total energy density of the universe like T to the 4th times some order 1 number. And so it would violate this bound, which is telling us that whatever is floating around that is not the Standard Model at that time should be less than 1 Standard Model neutrino. Of course, okay, this is very rough. You have to put in all the order 1 numbers, but it's parametrically okay. So you cannot have a dark matter mass that is much smaller than a mega electron volt and it's in kinetic equilibrium with the standard model at this time. So another bound that we have is the same, roughly the same quantity, but measured at the CMB time. So when the temperature was order 1 electron volt. And so if we write N effective, it's the total energy density in neutrinos divided by the energy density in one standard model neutrino. And we can rewrite it as the total energy density divided by that of photons if we rescale it, so by this amount. So this factor is just an order 1 factor that comes from those integrals that we have in the first day. So when you do the integrals over the equilibrium distributions of bosons, you have a +1 in the, sorry, you have a -1 in the denominator. For fermions, you have a +1. And so there is this order 1 difference between the two energy densities, so that of a standard model neutrino and that of the photon. But then, as we just said, weak interactions decoupled at a mega electron volt. This means that neutrinos at the time of the CMB are no longer in equilibrium with the standard model, and so their temperature is different than that of the standard model photons. And this is telling us what dark matter could do to disrupt the number of effective neutrinos during the CMB. So imagine that dark matter is coupled only to electrons and photons, but not neutrinos, or is more weakly coupled to neutrinos in such a way that after weak interactions freeze out, it's not significantly coupled to neutrinos anymore. In this case, if dark matter annihilations into the standard model or scattering with the standard model were still efficient after BBN, but before the CMB, then you would dump energy into the photons, but not in the neutrinos. So you would change this temperature ratio, and as a consequence, you would change what you measure as M effective. And the bound from the CMB is still order 1, but well, it's more kind of 0.2 roughly, okay, on the extra stuff that you can have. So you cannot change this temperature ratio by much because it enters to the 4th power. So even a small amount of dark matter energy dumped into the electrons and photons after the neutrino decouple is a problem. And in practice, so it's a bit more work to see how this bound works, but I can put a reference in the notes if you're interested. But in practice, if you work out what this means for dark matter, you still have the same bound, rough bound. And you can understand it from the fact that weak interactions are decoupling at this temperature. So whatever you do before, it's going to spread energy evenly between neutrinos and photons. Whatever you do after, it's going to potentially put energy into the photons and the electrons that is not going into the neutrinos, so it's changing the temperature. And so if dark matter is heavier than an MEV, it will have frozen out before neutrinos decouple from the standard model, and its effect will be negligible afterwards. If dark matter instead is lighter than the time when neutrinos decouple, it will freeze out later, and so its annihilations in the standard model will still be efficient between that time that we call BBN, so Big Bang nucleosynthesis, and the CMB time. So for the simplest models that we've seen, so those that were in chemical and kinetic equilibrium with the standard model, with the models that I've showed you, you cannot go below this rough lower bound. So, but okay, you can say, forget about coupling to the standard model. Let's play all these games in a dark sector. So who said that dark matter needs to be coupled to us in ways that are not gravitational? You can repeat the exact same calculation we did in a dark sector with its own dark radiation, let's say that this object, this dark sector is a bit colder than the standard model, so even if you have dark radiation, it doesn't contribute order 1 to delta N effective at either one of these times. Then, in principle, you're totally fine. But there is one last constraint that depends only on gravitational interaction that still kills you, but it kills you at a mass of below a kilo-electron-volt. So essentially, what's going on is that if dark matter is really completely decoupled from the photons, and it has some initial velocity, it will move around, okay? And on average, if everything is homogeneous and isotropic, modulo the small anisotropies that we see in the CMB, on average, this dark matter will just move equally in every direction. And so the net effect is that it will create a uniform gravitational potential. And this uniform gravitational potential is going to dilute these anisotropies or even wash them out completely. And as you've seen in Jay's lectures, these anisotropies seed galaxies. So without them, we wouldn't be here. And maybe more importantly, galaxies wouldn't be here. And so there is a strong observational constraint. So if dark matter in its life moves around more than a megaparsec, essentially there are no galaxies today. So this is a pretty robust, yes, observational constraint.
What about when dark matter has a strong set interaction with quantum computers?
Yes, so indeed there can be exceptions. There can be exceptions, although yeah, so I'm not sure about the numbers there. So if it exists a self-interaction that is strong enough to qualitatively change what I'm about to say. As far as I know, no, but I'm not 100% sure. I mean, because you should consider the fact that when dark matter freezes out, there are very few dark matter particles close enough to each other for this to be important. So you need a very long-range interaction comparable to the Hubble radius at the time when this stuff freezes out. And so this might be already excluded by observations inside the galaxy. So I cannot give a precise answer because I'm not sure of the numbers. But my feeling is that this bound will still apply. And so, OK, so to see how this bound works, you have to compute how much dark matter moves around, or what people call the free streaming length. So this movement of dark matter after it decouples from the photons is called typically free streaming, because these particles move around freely without interacting with anything. And so if you recall how to compute distances in cosmology, again, from Jay's lecture, this formula should be transparent to you. And so you have a power of the scale factor today, because this megaparsec number that I told you is the scale of galaxies today, roughly. And then you want to integrate between the time that dark matter is not anymore in kinetic equilibrium with the photons and the time it becomes non-relativistic, something that is moving at the speed of light. And then you have something that between the time it's non-relativistic until the time of matter radiation equality, it moves with some time-dependent velocity. And I'm putting here the time of matter radiation equality because after that, these anisotropies start to grow linearly with the scale factor due to gravitational interactions. So when matter starts to dominate the energy budget of the universe, these anisotropies start to grow fast. And so whatever survived until then, it will survive any dark matter free streaming. So the important point is that dark matter doesn't have to kill these anisotropies before matter radiation equality. And so, okay, the only trick you need to do this calculation is that you can write the velocity at some time t as the velocity. So at the time it became non-relativistic. So c redshifted to the time t. Okay, so that's if you use this relation, plug it back here, then the tools that I've given you and those that Jay has given you are enough to do this calculation. So if you want, you can convert the integral over time to an integral over a temperature using Hubble, and then you're going to find that the final result is something that looks like this. Times, so I'm going to go down here, a log. Okay, so and this choice of keV and electron volt are just such. So the electron volt is just the temperature at matter radiation equality. This keV number here is just a choice of normalization, so I get 1.1 megaparsec in front, which is comparable to the bound. So the bound is, I'm going to write it here, is something debated between 10 to the minus 2 and 1 megaparsec, depending on who you trust on your astrosystematics, because the observation, well, is mostly from Lyman alpha forest, and the systematics are mostly theoretical. Yes? What is what? Oh, this one, yes. So this is the time when dark matter is not in kinetic equilibrium with the photons anymore. So let's say the best case is that this happens way after dark matter becomes non-relativistic, so that this result is really when this time is after this time. So you need only to integrate between this time and t equality, this size of the equation. So let me be more precise here. So this is the general calculation, but the best case scenario, so the one that gives the most conservative bound, is when this time when you leave kinetic equilibrium is after that dark matter becomes non-relativistic. So you only have to do this integral. And then this integral will give you the result down here. And, well, yeah. So as you can see, completely decoupling the dark matter from the standard model is not even the best case scenario for this bound. But it's not going to, so if you do this to avoid the MEV bound, it's still going to give you a bound comparable to what we have here. Okay, so in the end, let's say that we take an upper bound on the free streaming length in between these two extrema, then we're going to get that you want a dark matter mass larger than a kilo electron volt, roughly. Okay? So the bottom line of this story is that in these thermal scenarios, as far as I know, you cannot go beyond this limit. Of course, okay, the whole spirit of the lectures, especially of these numbers, is purely illustrative. So it's to give you the concepts that allow you to go deeper. And there are all like research fields that are devoted only to understand which one of these numbers is correct. So there are a lot of details here that you're not seeing. But okay, I think this should be interesting for everyone. For those that are not too dark matter focused, it gives you the general ideas to appreciate what's going on. for those that are dark matter focused, I hope that it's giving you a way to think that's slightly different from the usual one that highlights the important parametrics. Okay, so, well, now there is an obvious question that we want to ask, which is, so why did I even bother writing down those experimental bounds on the dark matter mass if this is the whole story? So is there a way to break the kilo electron volt wall? The answer is yes, and so it's maybe not so obvious from what I said, but if you feel like it, you can try. So what's the crucial assumption here that it's making the bound not irrelevant? That it's important for thermal dark matter, but in principle, yes. Sorry, say that again. You should change.
The way it's produced.
That's true, but I want you to be more precise. So what's the part of the way it's produced that's making this bound relevant? So if you think about the physics of what's going on, there is, well, one quantity, say here, that you could set to 0, and the bound would be 0. So you're getting close. Okay, yeah, I also kind of realized it backwards, like by knowing how to make light dark matter, then I realized why this bound didn't apply. Yes, exactly. So these thermal production mechanisms all come with an initial velocity that is non-zero. So there is some kinetic energy floating around, and dark matter comes from it. But, okay, what if I can give you a simple way to make dark matter with 0 initial velocity? And that's what we're going to do now. And it's also, by the way, you should tell me when to stop. Sorry, 5 minutes? 7 minutes, okay, so I have time to do this. Okay, so the answer is that there is a simple way. And it's so simple that it's scary, because there is no coupling to the standard model at all. So presumably, if this is how dark matter is made, we will never know. Well, maybe we will, but not necessarily within our research lifetimes. So imagine that, okay, just have a scalar, okay, with the following action. A free scalar, even, okay? And let me imagine that his mass is very small, much smaller than a kilo electron volt, even say smaller than an electron volt, okay? Then I can ask, we know that the dark matter, what is fixed is the dark matter energy density today, okay? So naively, you know that if you make the mass small and keep the energy density fixed, the number density is going to become big. So at some point, as you make the mass smaller and smaller, you have to start wondering what's the right way of describing this dark matter particle. So as we said, below a kilo electron volt, it cannot be a fermion for the bound I told you about on the first day. So it has to be a scalar. But if you have a scalar with a huge number density, at some point it will become a classical field. So it's the same for the light in this room. So if you have a bunch of bosons in a de Broglie volume, they look exactly like a classical field. And so if we do the calculation, so we know from our beloved parametrics that the dark matter energy density today is roughly this number, and the temperature today is roughly 0.1 millielectron volt. We also know from the virial theorem that we debated a little bit on the first day that the momentum of dark matter in the galaxy is approximately this. So, okay, so I can ask how many dark matter particles do I have in a de Broglie volume? So I'm going to have n dark matter, so number density of dark matter times de Broglie volume. So the number density of dark matter is the energy density divided by the mass. And the de Broglie volume is just 2 pi h slash cube divided by the momentum cube. And if you plug these numbers into this equation, you're going to find roughly EV over mass to the fourth. So the moment this mass becomes a little bit smaller than an EV, you have a huge number of particles in a de Broglie volume. So a classical description is appropriate. So now, essentially, we're going to write down the same equation that you've seen for inflation with J, for solutions to the hierarchy problem with Gilad, but you will see that, well, the solution will be slightly different because for us, Hubble will be dominated by radiation and not by a cosmological constant. And so if a classical description is appropriate, well, the first thing that you want to do is to write down the classical equation of motion. But, okay, that you know already the answer. And if you haven't done it already, I suggest you derive this as an exercise starting from the action. Of course, this Hubble factor comes from the fact that we are assuming that our gravitational background is FRW and that the scalar energy density is too small to back react on FRW. So essentially you have a fixed gravitational background and you are looking at the dynamics of the scalar that has too little energy density to change this fixed gravitational background. So compared to what you've already seen, the only difference is that now our Hubble is dominated by radiation, so it's a function of time. It's not a constant. And that makes quite a bit of a difference because, well, like in the Boltzmann equation, there will be two regimes. There is a time when this term is much bigger than this other term, which in our case for the free scalar is just this guy. Oh, sorry, I should have put dot. And this happens roughly when Hubble is much bigger than the mass. Okay, because you can, so in an Hubble time is the relevant quantity because if you wait longer than an Hubble time, the universe has expanded and your parametrics have changed. So the way to get this estimate is to ask how much is phi changing in an Hubble time. So an Hubble time is 1 over Hubble. And so you're going to get that phi dot is roughly phi times Hubble. And so you're going to get that h squared phi is much bigger than m phi squared phi. And that's how you get this rough estimate. Okay, very rough. Don't try this at home. Okay, so in this regime, you can solve the simpler equation. And the solution is super simple. So phi is stuck. Okay? For us, the slow roll that you've seen in inflation is totally irrelevant. So phi is moving so little that, as you will see, it will not change the final amount of phi that we see in the universe. so initially phi is stuck, but, well, as usual, the universe is cooling down, is expanding, so Hubble is becoming smaller and smaller. So at some point, this will happen. And then, okay, you have to solve the full equation. But the full equation, well, you can see it by just staring at it, is a damped harmonic oscillator. The only, let's say, subtlety is that the damping term depends on time because it's decreasing with the temperature. But this can be solved exactly if, well, so there is actually at some point you should have complained, but maybe now you're so familiar with translational rotational invariance that you didn't want to complain. But here, this is not the equation of motion, right? Because there are also spatial derivatives in the action. So this is the equation of motion only if we make our usual assumption of homogeneity and isotropy, so that phi depends only on time. But, okay, this is consistent with the symmetries that we've been talking about over and over. And so, okay, finally, since this equation contains no spatial derivative, it's easy to solve. And it's going to give you something like this. Where these C0 and C1 are just integration constants. And if you plug, so now you can ask, what's the phi energy density that corresponds to this solution? Easy, you just calculate the stress energy tensor. That also I leave it to you as an exercise. And, well, I'm going to check the notes because I always get the factors of 2 wrong. I hope that I didn't get them wrong also in the notes, but you can correct me once you do the exercise. You're going to get this, OK? But this is an oscillating field. So what really makes sense to talk about is the average energy density, so averaged over many periods of the oscillation. And if you do that, so if you average these functions over many periods of oscillation, you're going to find that phi dot squared is equal to phi squared. Okay, this is kind of trivial if you look at this equation, but it's also a bigger fact in physics, so that, well, it's known under different names. And if you take this fact into account, you can write the average energy density more simply as m phi squared times phi squared, because the two terms are the same once you average. And so if you plug the solution down here, you're going to find that the answer is m phi squared, phi 0 squared over scale factor cube. Okay? This phi 0 squared is our initial condition. So if you remember, initially phi is stuck. So the initial conditions that determine these integration constants are that phi dot at the time where you solve this equation is 0, and phi has some initial value. Okay? So we are seeing 2 important facts. The first one is that this energy density redshifts like dark matter. So this very simple guy, completely decoupled from everything, free scalar, could be dark matter, right? So initially it's stuck, then at some point it starts oscillating, and its energy density redshifts exactly like dark matter. The second thing you see is that how much dark matter you have today depends on initial conditions. So if you compare the phi energy density today with the measured dark matter energy density, you're going to get something less illuminating than the case of the WIMP. So you're just going to fix the initial amplitude of phi, where this T oscillation is that time. So T oscillation is defined as this time. So if oscillation starts during radiation domination, which is a necessary condition, otherwise you don't have dark matter during the CMB, then this T oscillation is going to be roughly square root of m phi m Planck. So if you want, you can plug it back here to get nicer parametrics. But the fact remains that how much dark matter you have today depends on initial conditions. Well, you could say that this is less nice than a WIMP, but you cannot discard this possibility based only on this fact, especially because nature disagreed with us multiple times on what's nice and what's not nice. I mean, if you just think about grand unification. I mean, for me, grand unification is the best example of this, because we really have no other explanation of the charge ratio of the electron and the proton, but nature doesn't seem so much in a hurry to realize the simplest grand unified models. Okay, but setting this aside, what we've just learned is that you can have an extremely simple dark matter candidate that doesn't respect any of the intuition that we had from thermal production. And this guy is consistent with the free streaming bound I showed you before for this reason, that we essentially set to 0 its spatial derivatives, meaning that effectively when we talk about this classical solution, we're talking about an object that has 0 velocity. So this guy is not free streaming anywhere. It is moving in its potential, right? So if you want, the picture is that phi has some initial position, is stuck there for a while, then it starts oscillating around the minimum with smaller and smaller oscillations that are damped by the expansion of the universe. But okay, this is a velocity in an abstract theory space, so it's not the velocity in the real space of our universe that can damp structure. So I think that this is a good place to stop. And tomorrow we're going to see that this nightmare scenario could actually be realized by a particle that solves another problem in the standard model. Actually, potentially, that solves 2 other problems in the standard model, which is the axion. And so we're going to see how the axion explains the smallness of the neutron electric dipole moment. We're going to see why it's weird that the neutron electric dipole moment is small. And then we're going to see how the axion can, at the same time, be dark matter, explain why the neutron electric dipole moment is small, and maybe, if we have time, even see how it can solve the hierarchy problem. All this in one go. Actually, you need 2 axions, but I think it's still pretty good for 2 degrees of freedom. All right, so if you have questions, I'm here to take them. If not, I'll see you tomorrow. Yes?
Questions before break?
Yes? Yeah, so phi naught will depend on the mass. So if we, let's say, finish our estimate, you're going to have m phi squared divided by electron volt times m Planck m phi to the 3 halves times phi naught squared. So this, we want the ratio between the phi energy density and the dark matter energy density today to be order 1. And so phi naught is roughly going to be, so let's see. So there is, let me not mess this up. So there is m Planck to the 3/4. And then there is 1 over m phi times m phi to the 3/4 times electron volt to the 1/2. So this is roughly m Planck to the 3/4, m phi, so electron volt to the 1/2, m phi to the 1/4 at the denominator. Okay, so it's not very illuminating, but if you give me a mass, I can tell you what phi naught should be. If you want, okay, if we put really the numbers, so this is 10 to the 19, so this is roughly 10 to the 15, so this number here is roughly 10 to the 15 GeV. 10 to the 15, sorry. So 10 to the 15, so it's not GeV, but it's GeV to the 3/4. This number is electron volt to the 1/2. So if we convert everything, this is going to be, so I wonder if I made a mistake here, but let's see. This is electron volt to the 1/2, that's fine. So 3/4 is fine. Phi it's also fine, so it's looking okay. Yes, so finally, you have 10 to the 9 to the 3/4, so that's roughly 10 to the 6. So you have 10 to the 21 EV to the 3/4 plus 1/2 over m phi to the 1/4. And so this is giving us roughly 10 to the 21 EV times EV over m phi to the 1/4. So if we want it in GeV, this is so this is roughly 10 to the 12 GeV for an electron volt mass. So it's telling you that the fundamental scale of the, actually it was a very interesting question because it's telling you that there is a huge hierarchy of scales between the mass and the fundamental scale of the potential. So sorry, yeah, can you come closer or talk louder because I cannot hear you very well. How small m phi should be so that phi? Yes, so already, so when this number is bigger than 1, so when this number is much bigger than 1, this is the correct calculation. So when the number of phi particles in a de Broglie volume is much larger than 1, this classical description is okay. So essentially any m phi is much smaller than an electron volt or even a little bit smaller than an electron volt is fine. So this dark matter, this can be dark matter all the way down to the observational bound of 10 to the minus 22, 21 electron volts. Yeah, sorry, I answered the question that I wanted to get instead of the question that you asked. Sorry.
Okay, let's close it there and take coffee. And thank Raffaele.
I think I did better in not switching blackboards too much. Yes.
I have a quickly question.
Sure, sure.
Why do you say that when you have this question, this is sort of